Quantum mechanics studies the smallest particles in the universe, like electrons, protons, and photons. Unlike classical physics, it deals with phenomena at the atomic and subatomic levels, revealing a world where particles can exist in multiple states at once. For example, particles can be in two places at the same time and instantaneously affect each other over vast distances. Scientists like Albert Einstein and Niels Bohr have contributed to our understanding, leading to advancements such as semiconductors and lasers. Despite its complexity, quantum mechanics continues to intrigue and challenge our understanding of reality. In this essay, we will delve deeper into concepts like superposition, wave-particle duality, Schrödinger's cat, and quantum entanglement. By the end, you will see how quantum mechanics reshapes our view of the universe. Superposition means a particle can exist in multiple states at once. For example, an electron can be in two places simultaneously or spin in two directions at the same time. Imagine flipping a coin. In the quantum world, it can be both heads and tails until observed. This state of being in multiple possible states simultaneously is called superposition. One famous example is the double-slit experiment, where particles like electrons create an interference pattern, suggesting they go through both slits at the same time. Superposition challenges our everyday understanding of how objects behave, showing that, at the quantum level, reality is not as straightforward as it seems. Particles exist in a cloud of possibilities, and only when measured do they settle into a definite state. Wave-particle duality states that particles, such as electrons and photons, exhibit both wave-like and particle-like properties. Light behaves both as a wave and as particles called photons. When light passes through a prism, it bends and spreads out like a wave. But when it hits a metal surface, it knocks out electrons as if it were made of particles. Louis de Broglie proposed that particles such as electrons also have wave-like properties, confirmed through experiments. When electrons are fired at a crystal, they create a diffraction pattern similar to waves. This wave-like behavior is crucial for technologies like electron microscopes. Wave-particle duality means that particles can interfere with themselves, creating patterns seen in the double-slit experiment. It also means that particles do not have definite positions until measured, existing as probabilities spread out like waves. Understanding this dual nature helps scientists develop new technologies and explore the fundamental nature of reality. Schrödinger's cat is a famous thought experiment illustrating superposition and the role of observation in quantum mechanics. Imagine a cat inside a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the Geiger counter detects radiation, it breaks the vial, releasing the poison and killing the cat. If no radiation is detected, the cat remains alive. According to quantum mechanics, the radioactive atom is in a superposition of decayed and not decayed states until observed. This means the cat is simultaneously alive and dead until someone opens the box and observes it. Schrödinger's cat highlights the paradoxes of quantum mechanics and the importance of observation. Until measured, particles exist in a cloud of probabilities, and observation collapses these probabilities into a single, definite state. This concept is known as wave function collapse, and challenges our understanding of reality. The collapse of wave functions describes how particles transition from a state of superposition to a single, definite state when measured. In the quantum world, particles exist as a wave function, a mathematical description of all possible states they can be in. When a measurement is made, the wave function collapses, and the particle settles into one of these possible states. The famous double-slit experiment demonstrates wave function collapse. When electrons are not observed, they create an interference pattern, behaving like waves. However, when observed, they behave like particles and create two distinct patterns. The act of observation collapses the wave function, determining the electron's position. Understanding wave function collapse is crucial for developing quantum technologies such as quantum computing. In quantum computing, qubits exist in superposition until measured, and manipulating these qubits without causing wave function collapse is essential for building powerful quantum computers. Quantum entanglement occurs when two or more particles become linked, such that the state of one particle instantly influences the state of the other, no matter the distance between them. Albert Einstein referred to entanglement as spooky action at a distance. Experiments have repeatedly confirmed the existence of entanglement. When two photons become entangled, measuring the state of one photon instantly determines the state of the other, even if they are light years apart. This instantaneous connection defies classical physics and suggests a deeper underlying connection between particles. Entanglement challenges our understanding of space and time, suggesting that the universe is more interconnected than previously thought. It also has practical applications in quantum computing and cryptography. Quantum computers use entangled qubits to perform complex calculations at unprecedented speeds. Entanglement illustrates the intricate and non-local nature of the quantum world, showing that particles are part of a vast, interconnected web. Quantum mechanics poses profound questions about the nature of reality. At the quantum level, particles do not have definite properties until measured, existing in a state of possibilities described by a wave function. Superposition means that particles can exist in multiple states simultaneously. Wave-particle duality shows that particles have both wave-like and particle-like properties. Quantum entanglement reveals that particles are interconnected across vast distances. These phenomena suggest that reality at the quantum level is fundamentally different from our everyday experiences. Some interpretations of quantum mechanics propose that multiple realities exist simultaneously. The many worlds interpretation suggests that every possible outcome of a quantum event exists in a separate, parallel universe. The role of observation in collapsing wave functions raises philosophical questions about the nature of consciousness and reality. Quantum mechanics challenges our understanding of what is real, revealing a universe that is far more complex and interconnected than we ever imagined. Quantum mechanics may seem abstract, but it has practical applications that impact us daily. Many technologies we use today are based on principles of quantum mechanics. One of the most notable applications is in electronics, with semiconductors and transistors relying on quantum principles. These components are the building blocks of modern electronic devices, including computers, smartphones, and televisions. Another application is in medical imaging, with MRI machines using quantum principles to create detailed images of the body's internal structures. MRI relies on the behavior of atomic nuclei in a magnetic field, a phenomenon explained by quantum mechanics. Quantum mechanics also plays a role in cryptography, with quantum cryptography using entanglement and superposition to create secure communication channels. Quantum keys are virtually impossible to intercept or decode, providing a high level of security for sensitive information. The principles of quantum mechanics are embedded in many aspects of modern technology and medicine. Quantum computing is one of the most exciting applications of quantum mechanics. Unlike classical computers, which use bits, quantum computers use qubits. Qubits can exist in superposition, representing both 0 and 1 simultaneously. This gives quantum computers a significant advantage. They can perform complex calculations at unimaginable speeds. Problems taking classical computers thousands of years could be solved in seconds. Quantum computers use entanglement to link qubits, processing information in unique ways. Major tech companies are investing heavily in quantum computing. Quantum mechanics has been shaped by the contributions of many brilliant physicists. Niels Bohr was a pioneer in developing the early foundations of quantum theory, introducing the idea of quantized energy levels. Albert Einstein, although skeptical of some aspects of quantum mechanics, made crucial contributions, such as his explanation of the photoelectric effect. Erwin Schrödinger is best known for his wave equation and his thought experiment, Schrödinger's cat. Richard Feynman was a key figure in developing quantum electrodynamics, or QED, and his innovative approach to visualizing quantum interactions revolutionized the field. These physicists, along with many others, have shaped the field of quantum mechanics, and their contributions continue to influence research and inspire new generations of scientists. Quantum mechanics is evolving with new discoveries and advancements. Quantum computing is a key focus, aiming to build practical quantum computers. This involves developing stable qubits, error correction, and scalable architectures. Quantum communication uses entanglement for secure channels. Quantum sensing achieves unprecedented precision in measurements. The future of quantum research will uncover new phenomena and applications. The journey into the quantum realm is just beginning, shaping the future of science and technology.